All right. Well, welcome to this last session of day 2, lecture number 9. And I know we're all a little bit tired, so I'll try to make it interesting and a little bit entertaining. This talk is a little bit tangential to the program of the conference, because suddenly we're talking about continuous choices. Okay. But the idea is that, you know, the big point that I want to make is that understanding how the algorithms work can take you a long way in solving complicated models and, you know, being able to do structural estimation. That's one point. Another point, if you happen to have a problem that fits this class of problems, this is by far the best thing you can do in terms of computations. And therefore, it's a really nice trick to know and have in your toolbox. All right, so let's first agree that, you know, discrete choices and continuous choices come together in our models all the time. How much to work, when to retire, how much to save, when to buy a house, right? Which car to buy and how much to drive. Sometimes the discrete choices can be separated from the continuous choices and the model simplifies. So like in the last case here, in the paper that Bertel talked about this morning, there was driving, which is a continuous choice. And yet by assuming that driving does not affect the evolution of the car, right? It's just the age, then we could separate the continuous choice into its own kind of static form. And so, you know, what do we do usually? Usually we just sort of disregard the fact that these choices are coming together and transform the model into either continuous or discrete choice framework. Is this thing working? Well, there's a good reason that we do that. The reason is that the combination of discrete and continuous choices in the problem makes it pretty hard. So you will see through this talk that the problem becomes non-concave. The first order conditions then obviously are not sufficient. We have to do something more. If we're thinking about the dynamics, the value functions suddenly have kinks. The policy functions have discontinuities, and you get all sorts of this, you know, fun stuff. That means that applying normal approaches becomes much, much harder. So for example, we suddenly need a global optimizer to find the optimal action in each point of the state space, just because the problem is not concave. We sometimes have to keep track of where these kinks and discontinuities are to simply facilitate numerical methods like quadrature, for example. Because, you know, for some numerical methods like quadrature, we assume smoothness of the functions that we're working with. And so other numerical procedures may have to be adjusted as well. Anyway, so all this leads us to the set of methods which are evolving around the idea of endogenous grid points. Right, so the plan today is that we first talk about plain vanilla EGM, endogenous grid point methods. Then we will add discrete choices, and we kind of follow the how should I call it? You know, the thought process that we had. And I mean, we can admit that it's been a long journey. But first, you know, we're trying to just extend the ideas of EGM to the models which also have discrete choices. And then, you know, adding our favorite taste shocks with extreme value distribution turned out to be a really nice approach that allowed us to work with these nasty problems in a much more manageable way. All right. And then I also want to say some words about how the class of the models that are solvable by these methods can be expanded. And in particularly, multi-dimensional generalizations are very appealing, but they're hard. All right, so method of endogenous grid points. That's essentially a very fast and very accurate method for solving dynamic stochastic consumption savings problem in its original form. It will work with finite and infinite horizons. The examples that I will show you will kind of assume finite horizons, but I'm a little bit vague about that, and that's because they're totally applicable to infinite horizons as well. One important assumption is that the utility function is going to be nonlinear and differentiable. And then it would also be very nice to be able to analytically invert the marginal utility. In the standard formulation, we will have one continuous state variable, wealth, or think of this as wealth, and one continuous choice variable, consumption. And so we're in the very standard consumption savings model that John Stakarsky was showing you on the first day. There will be a particular structure of the law of motion of the state variables, or this state variable wealth, and you can all think about what that's, law of motion is. It's very standard, but it will have to have a property that we sort of base this whole approach on. And it turns out that we can accumulate at least simple borrowing constraints pretty efficiently. All right, then the expansion to the discrete continuous problems, we still have to have strictly concave and monotone differentiable utility functions. We can have that continuous state, which would take the role of wealth, but also add additional discrete state variables if we need. Okay, so that's kind of not a real restriction, except that the transition probability for these additional states will have to be independent of M. And then we still have this one continuous choice variable with one discrete choice variable denoted dt, where of course one discrete choice variable really means any discrete choices, because you can map multidimensional discrete choice into this one-dimensional thing. All right, and then we will have two flavors of this model, as I already mentioned. There's going to be one without taste shocks, so everything will have to be deterministic in some sense. And then we add this smoothing device of the extreme value shocks to make the model more manageable. Learning outcomes, that's for this talk. If you have one continuous choice of consumption and additional discrete choices, use DSE2022AUS. That's very simple. If you're working with a model which has one continuous and some discrete choices on top of that, EGM or DSE2022AUS version will just going to be much more accurate and quick compared to other methods. The reason is that this approach essentially avoids the root finding steps in the solution algorithm. So instead of doing tedious iterative equation solving, you're just calculating the solution of the problem directly. I'm saying that if the utility is separable in continuous discrete choices, then kind of standard credit constraints are also handled by the method really efficiently. And then if you can allow for extreme value shocks, then the problem becomes much more manageable. And we're mentioning in the paper that you could either think of this extreme value shock as something structural, like we usually do, right? Some additional information that the decision maker knows, but not the econometrician. Or you can think of this as purely numerical smoothing device. And then by adjusting the amount of the smoothing that you include into the problem, you can actually approximate the deterministic version of the model as well. I guess I shouldn't point on the slides there for the online audience. All right, so any questions so far? Hope I made you interested, making a lot of promises. How many people, by the way, have seen this before, have worked with the GM? I know there are some in the audience. Okay, hopefully it's going to be somewhat useful for you guys as well. All right, so let's start with the standard consumption savings Phelps formulation. We have a Bellman equation here, right? One state variable MT, that's your wealth. You're consuming out of that wealth, so the choice variable C is between 0 and MT, and you are getting the instantaneous payoff U of C plus the discounted expected value, all very standard. The intertemporal budget constraint is essentially what you haven't consumed today times some return, right? Deterministic or stochastic return on savings. Let's keep things simple, start with deterministic return, but then, we can write expectation and have that be stochastic as well. I'm going to assume that the utility is CRA, and logs in some special cases. Well, this problem, as many of you know, has an analytical solution, which is written right here. And what do we see here? With this intertemporal budget constraint, the optimal policy, the optimal consumption rule, the policy function is just linear function of M. So at any time, you're taking some fraction of wealth to consume in the period. And as you can see, there is capital T here, kind of making you think that this is a finite horizon problem. All right, just to make sure that we're all on the same page, in finite horizon problem, the solution is a collection of value functions, right? And the value function corresponding to the last time period, it's somewhere here. Oops. This one, the bottom one, right? And the value function corresponding to the optimal choices in this life cycle model in the first time period is somewhere on the top. And then this represents the policy functions, the optimal consumption rules, with the top line showing being the 45-degree line. That's basically your final time period, right? You consume everything you have. That's the optimal thing to do. Otherwise, depending on the period, there are other policy functions. Now, here's a question to make sure that you're not sleeping. Where's the solution of the infinite horizon problem? Yeah. Say it again. Say it loud. So the top one. Okay. Well, in the value function space. Right, you can think of this as being just an arbitrary guess for the value function where we started the value function iterations. You know, the theory applies, it's a contraction mapping, the Bellman equation or the Bellman operator, and then we just converge. And you can see the convergence kind of going to the top of the value function. And same thing with the policy space. You start with an arbitrary guess of the policy function. As you iterate the Bellman equation, kind of things can converge to the bottom policy function here. All right, let's make things a little bit more complicated and add this stochastic return, right? The y tilde, and suddenly the problem doesn't have the analytical solution anymore because the intertemporal budget is complicated by the presence of this stochastic return, stochastic income that this person is getting every time period. Everything else is the same. And so let's think about how do we solve this problem now. And I want you to think of this continuous choice variable, the C over there, as being truly continuous. Okay, so I don't want to discretize consumption. What do I do if I don't want to discretize consumption? Well, we can still write value function iterations. We can successively approximate if it's an infinite horizon. In the finite horizon, we just calculate value functions starting with the capital T, where the value function is just the maximum utility. And the answer, of course, is very simple here. Utility is monotone increasing, so you just consume the whole MT in the last period. But in the periods before that, we're solving the Bellman equation, essentially, right? Now, to solve it, like I said, I don't want to discretize, so I will have to use some sort of a solver, a Newton method, for example. And so I thought that I would have time to show the code. Probably I do. Yeah, you know, we're kind of agnostic to the language choice here. And so there's a MATLAB version on the repository. Where would that be? Oh, sorry. I thought I set it up so that I have a separate screen here. But I guess I don't. So the repository for the course would be here, right? Everybody has access to this internal page, right? With the links to all the necessary things. And I really hope you can also make use of the list of the participants. And so I'm looking at the code in this directory 09. In code, you can see MATLAB and Python implementations. They're slightly different, but convey the same ideas, right? So I'm going to be running this code here. And so if we look at the code, there is something called model DSE, and it's an example of using MATLAB way to write classes, right? The object-oriented approach in MATLAB, which is also possible. And so this module defines the model and all the necessary methods to solve it in this one file, and we're just going to run it using this additional script, where the model is created in the beginning, and then I'm just going to employ this method of the object solve VFI. All right, and I'm running MATLAB here in the terminal. And you know, each dot here is drawn every time a particular point in the state space in a particular time is solved. And in order to find that optimal consumption in this code, I'm using Newton method essentially. And you can see, you know, with 25 periods and so many points in the state space, we get the solution, which looks like this. And you can see that now I hope you can see all of these. Now the policy functions, they are not linear because of that additional income, which was deterministic, by the way, in this setting. There's this period or this interval of wealth on the horizontal axis where it's optimal to consume everything you have. And that's really because you know that next period you will get some additional income. And so, you know, you can afford not saving anything for the small values of wealth. Okay, does it make sense? All right. Okay, that's the VFI solver. It's pretty straightforward, right? So just to make sure that we're all on the same page, let's derive an early equation, which is just the first order conditions for the maximization problem in the Bellman equation, and then an additional use of the envelope theorem that brings you to the expression which leaves you with this conclusion that the marginal value function or the derivative of the value function with respect to wealth is exactly equal to the marginal utility calculated at the optimal choice of consumption. We can move that forward by one time period and plug that expression in to the original first order conditions to get the early equation that we're all familiar with. And then we could also use early equation, right, to approach the solution of this problem instead of doing VFI, and only work in the policy space. And so what do? Again, we fix the grid over wealth, over our M. So we fix the points of wealth where we will solve the problem, the consumption problem. At the terminal period, the policy function is the argmax. Again, it's very simple. And then we're doing backwards induction and solving the early equation, now written like this, solving the first order condition by plugging in the optimal consumption one period ahead. And so this is an equation in CT, right? CT comes on both sides, and we solve that equation for a pre-selected grid over MT, which also is part of the equation. Now, do you think this was going to run faster? Any opinions? Wending? Will it run faster or not? Not faster. And the reason, of course, is that instead of maximizing solving the maximization problem, we're solving the nonlinear equation, which is essentially the same complexity. And we're also doing that in each point of the state space M. And again, we need some sort of iterations here in order to solve the equations and spend time. I don't have the code actually. That was one of the tasks for you to do. All right, so here is the promise of the EGM. What if we didn't have to solve this equation? What if we didn't have to do any sorts of iterative algorithm in order to calculate the optimal consumption in each point of the state space? Well, it turns out to be possible. And so, the paper which brought it into economic light is this Carroll 2006 economics letter, very short paper. The idea, which is the idea of EGM, is that instead of searching for the optimal decision in each point of the state space, which is our traditional approach, let's try to look for the state variable, the value of the state variable, where some kind of arbitrary chosen level of consumption turns out to be optimal. So we're turning this, the problem inside out. Instead of fixing the wealth, the point in the state space, and then searching for the optimal consumption level, let's just guess some consumption level. Just take any number, right? And find the points in the state space, the wealth, where this chosen number is going to be optimal. Okay, does it make sense? It's kind of magic. So here's the algorithm. First thing to note is that algorithm is still backwards induction. Okay, so we start with capital T. In capital T, in this problem, solution is very simple. We just consume everything, and then we're going to iterate in the backwards induction fashion. So imagine that instead of fixing a level of consumption, I fix the level of what's left after consumption in each time period, and I'm going to call that A. So let's say this is current period savings. Okay, this is what's left after consumption in the current period. And we know that that's actually the difference between what we had in the beginning and what we've consumed in the current period. Well, knowing A, and given the structure of the intertemporal budget constraints, I can actually compute how much money I will have next time period, right? Because this is just going to grow with the interest rate, potentially stochastic. And that means that if I already have the optimal consumption function, the policy function for the next time period, I can compute the optimal level of consumption in the period T+1. Okay, right? But then we have the early equation. Now imagine that the marginal utility is invertible analytically, and that's going to be the case for CRRA and log and many utility functions. Well, then I can compute the right-hand side of the early equation as a conditional on A, which I've chosen in the very beginning, and then invert that and get the level of consumption in the current period, which is optimal given the amount of savings, right? Because this is just the first order condition. Okay, last step. Well, we said that this is A is what we are left with in the end of the period. And we just computed the optimal consumption. So at which level of wealth is this all optimal? Well, you just put them together and find the level of wealth in the current period to which the chosen savings and the computed consumption is optimal. Right? You can see that we started with the guess of A and we ended up with the MT and the corresponding CT. So we basically put these numbers together, and going point by point through some grid on A, we just reconstruct this function or the approximation of this function. This feels like magic if you haven't seen it before. And I can tell you, it took me, I don't know how many times to go through the steps of this algorithm to actually understand what's going on. So let's do it again. So imagine that we fixed a grid on A, okay, which is the end of period savings. And we're doing backwards induction. We already know the policy function in the next time period. That's the C star of T+1. And we fixed the end of period savings, the A, and we're going to go through many values of this A, right? It's going to be many values of this A that we do this step for. Okay, we have A. Now we can calculate the MT+1, how much money I will have in the next period. That's just because of the structure of the intertemporal budget constraint. It's whatever you're left with times the 1 plus R, right? Times the growth factor. Okay, now I know how much money I will have in the next period. And I also already have computed on the previous step of the backwards induction, I've computed the optimal level of consumption corresponding to that amount of money. Right, I already have the policy for T+1, so I can compute the optimal level of consumption in T+1. And then, using the early equation or the inverted version of the early equation, I can make a link from the optimal level of consumption tomorrow to the optimal level of consumption today. That, together with A, gives me my points in the state space, my wealth today, to which the computed level of consumption is optimal according to the first order condition. Okay, and so by going through a list of A's, I can construct many different optimal levels of consumptions corresponding to many different levels of wealth in this period. And that is nothing else but approximation of my policy function in the current period. And then I'm ready to do the backwards induction step and go to the previous period and now use this function, the C star of t, in order to perform the same step again in the previous period. And that allows me to continue backwards induction all the way to the first period if it's finite horizon, to all the way to convergence if it's infinite horizon period. You had a question. Fine. And I didn't say anything about borrowing constraints so far, right? So it's totally applicable. Where's that? Yeah, in the model, but not here. So right, that's correct. So of course we're thinking about the inner solutions here with the Euler equation. In the absence of credit constraint, it's going to be even simpler because Euler will hold everywhere. But in the presence of credit constraint makes it somewhat more complicated. And we'll talk about credit constraint in a moment. But if you don't have the credit constraint, that means that A can be chosen anywhere, right? You could end up with negative savings. And so you just use the grid over negative values and positive values to perform this step. The step is the same. Let's come back to that. We're going to talk about that in detail in just a minute. Right, so, you can go through these steps like I did many times to think more about the algorithm, but many of you would realize right away that what we're actually doing is we are reconstructing the C of M, the policy function, as a parametric curve, okay, with the parameter A. So we're choosing A as a parameter, and we're performing this inverted Euler equation calculation to reconstruct the points C and M that together give you the function or the correspondence in principle, but hopefully a function which is a policy function. And for that, you have to know the C naught, which is the kind of previous iteration approximated policy function. Okay, and nothing else is happening here. We're just going through the grid of this A as a parameter and reconstructing these pairs of points. And these pairs together give you the optimal, or describe the optimal consumption savings behavior. Okay. Now, is this complicated? No. This is the minimal implementation in MATLAB. It does rely on a few functions, but this is 11 lines to completely solve, full-blown stochastic consumption savings model. And this is in the repository. This is really, quite simple. How fast is that? That's astonishingly fast compared to other approaches where you would want to find the optimal action, right? The optimal consumption in every point. Let's actually see that. So I was running VFI, and you remember, it takes some time. We have to wait a little bit, but let me just switch this. There's an ad hoc way of switching different parts of the code here. I'm going to solve the same problem with the EGM, right? Oh, and there we're done. It was pretty fast, wasn't it? Do it again, it's done. Now, this solved it 100 times. Every time I press the button here, I'm solving hundreds of these problems. And, one solution takes 0.02 to 0.002 of a second compared to about 6 seconds before. So the speed up is absolutely amazing, as you would expect. Now, what about the accuracy? Well, you can see, the maximum absolute error in the consumption function if you solve through early equations, trying to pinpoint, right, the early residual to be 0 is still, somewhat higher than what you get with EGM, essentially doing the same thing, but in the different sets of points. So this is speed up without loss of accuracy, which is quite astonishing. That's not something that we see very often. All right, let's talk about credit constraint now. So it turns out that with monotone and concave utility function, you can show that the end of period assets, this consumption function A, is non-decreasing in M. Okay, in presence of credit constraint. Of course, you can't use the early equation to describe the solutions which are corner solutions where this binds. But what you end up doing is that, with the credit constraint, you cannot have negative savings. So the lower A is 0, and you can compute with A equals 0. You just perform the EGM step, and that gives you some number, some value of wealth, all right, that corresponds to the optimal not saving anything. All right. Now, because you have this the monotonicity, that means that if you go lower on M, right, the A, corresponding A, cannot increase. Right, but it can also not decrease because you're already at the restriction. So what ends up happening is that you recover this point of M. Now this is M on the horizontal. Wealth is on the horizontal axis here, and optimal consumption is on the vertical axis. So I've taken the 0 savings, and that gave me this level of wealth where 0 savings is optimal according to the first order condition. And I know that because of monotonicity, everything lower in wealth requires even lower savings, but we can't go below 0. And that means that everywhere here, optimal savings is 0. We are at the corner. What does it imply for consumption? Optimal consumption is a 45-degree line. All right. So, standard credit constraint is really easy to do. You just put additional line on the grid in the origin. It also has other implications. Imagine that we did not do this endogenous grid and did not compute these points on wealth as endogenous points. But instead, we would put some exogenous grid on wealth, which is on horizontal, right? And calculated the optimal level of consumption for each of those exogenously fixed levels of wealth. And if we, employ really nice computational methods, low tolerances and such, we would get, this curve we would get somehow, and hopefully we would also be able to reconstruct the corner solutions. And so we would have points on this part as well. But it's going to be extremely hard, if not impossible, to put a point here, where this optimal consumption profile, the policy function, kind of deviates from the 45-degree line. Because you have to do that, you would have to put up front a point on the wealth space exactly where this kink is. All right? That's going to be very hard because the kink also moves as we do time iteration, so as we do the different time periods. What that implies is that now you have an approximation to the optimal policy function in different time periods, and doing simulations, you will inevitably accumulate some error when you're using approximations of the policy functions. Okay, especially around here. So around this kink, the policy function computed on the fixed grid of wealth will not be fully accurate. Now, as you will see, we will have to calculate the value function in order to move forward. And so how do you calculate the value function with EGM? Well, once you know the optimal consumption, it's kind of easy. You plug it into the Bellman equation. But for this area where we will not have any points close to the origin, because we've just connected the dots, it would be nice to know that the value function is given by just this expression. Why? Because we do know what's the optimal consumption level is. it's optimal in the credit constraint region to consume everything you have and to leave zero essentially for the future or for the next period. And that means that suddenly in this region, we have an analytical expression for the value function, no problems whatsoever. We can calculate value function as approximated on the region where we are generating this endogenous points, or have the analytical expression closer to the origin. All right, any questions for EGM part? How much time do I have? I have about 15 past, right? So let's try to do the EGM with just discrete choices. So I guess one paper I will point to is our paper in QE, where we do this DSE EGM that I will be talking about. And as I said, there's going to be two flavors, with and without the extreme value shocks. But really, the credit should go to Julia Fallow, 2014, who had looked at the non-concave version of EGM, including the discrete choices. And the approach there was to use global optimization methods, right, inside of the area where the first order condition is not sufficient, where problems are, and then use EGM on the outside of those regions. And so the application here is to find and compute the regions where EGM is applicable as it is, and do something else. We are doing a slightly different approach, actually. All right, so to fix ideas, let me now look at this simple retirement model. We want a combination of consumption and something discrete. Well, let's think of something very simple, discrete. It's just going to be a decision to retire, okay? To make things even more simpler, I'm going to say that if you're retired, and this is denoted by the second argument in the value function, this is your state, right? You're either worker or retired. So in the state of retirement, there's no further discrete choice. You just retired forever. So retirement is absorbing. Then you're solving the consumption problem that we have already discussed. And I don't have to sort of look at this state. Now, is this essential? No, you don't have to have an absorbing state. That's the question that usually pops up. This is just for the easier demonstration of the method. Okay, if you're a worker, then there is a choice of remaining to be a worker or retiring. And therefore, we have these two expressions here written as a maximum, right? That's the discrete choice of retirement and staying at work. In case you remain to be worker, then you have a special punishment, right, in the utility function, the disutility of work, which is going to say that's an indicator. If you're working, you're getting some punishment in utility terms, but instead you're getting some salary, some wage over here. And you can see here the timing assumption that the wage comes next period. It's not really that important. All right, so that's the modification of the problem. And both, of course, worker and the retiree, they choose optimal consumption. And believe it or not, in this formulation with deterministic income, deterministic wage, right? That's the condition. We can write an analytical solution as well. And this is going to be very, very useful because now we can try to match the analytical solution with our numerical methods and see how much, can we even recover it? And if we can, how much the numerical error is. Okay, it looks like this. I'm showing here the optimal consumption functions, right? The policy functions. As you can see there, they have funny shape and they have different number of discontinuities in different time periods. So if you're close to the capital T, to the end of the life cycle, you tend to have less discontinuities in the analytical solution. And in capital T, of course, you just consume everything as before. So if in capital T, this is just a 45-degree line as before, nothing changed there. That's actually because of our timing assumption that wage comes next period. What can you say about this? It's very important not to confuse this picture with the simulated consumption profiles. We have cash in hand, so wealth on the horizontal line here, and what's the optimal amount of consumption shown by different graphs, okay? But this doesn't mean that, if I move my consumption and looking at this red line from 200 to whatever, 190, I'm going to be consuming more. Well, if it happens to be this difference in the simulation, then my consumption would change. But the discontinuous optimal consumption functions, the policy functions, do not necessarily imply anything about the shape of the simulated consumption path. Moreover, these are drawn for the deterministic case. And as you will see, our agents are going to be hyper-rational. They will be computing these crazy functions, the optimal rules, and jumping between the discontinuous portions of these consumption functions in order to do the same thing, in order to smooth the consumption profile. And for certain parameter values that you would most likely know, you can actually get a flat consumption profile even with these things. By the way, I guess I've forgotten to show the example here. In the code, we can run this test and try to simulate consumption paths. You would see here that I'm setting the discount factor to be exactly 1 over 1 plus the interest rate. And if you do the math, this is a deterministic model. The Euler equation ends up being that you just want to have the same level of consumption in every time period. Okay, and solving with VFI, we can see. Okay, we have to wait a little bit. Sorry. That's again because the reason that we're using the Newton solver for every point of the wealth state space is to get very accurate solution, right? Discretized solution has no chance of producing flat consumption profiles because you would be jumping about the optimal choice of consumption every time. But even here, you can see that, even though we started with something pretty flat, by the end of the life cycle, things go ballistic. Why? That's because the error accumulates. So small errors in the policy function accumulate over the life cycle. All right, let's do the same with EGM.
Make it flat.
Oh yeah, and there is a good story that's working on this method. I was a postdoc with Michael Keane, and he was not quite convinced that this works, right? And so he came up with this test, which is simulated consumption profiles. And he would say, let's just set the discount factor to 1 over 1 plus R and simulate consumption. If your method works, then they will be flat. And they were almost flat. And, he would say, no, they're not flat. Go back and find the bug. And so it took some time. But you can see they're flat. In the end, they're completely flat. And I'm drawing two, so I'm cheating a little bit because if you just look at one line, then MATLAB will draw it to be a little bit jagged because of the numerical noise. But the difference here is this is 674 and that's 688 is really small. So, for all practical purposes, they're really flat. Mike was satisfied. And what I was saying is that even with these policy functions, as we will see, the consumption profiles can be very flat as well. So our consumer, our decision maker, starting from any level of cash in hand in the beginning of life cycle, would calculate this such that, taking into account the temporal budget, the simulated profile jumps between these discontinuous sections and produces a completely flat profile in the simulation. All right, but in order to get this numerically, let's try to reconstruct the steps that we took some years ago. The idea was that, okay, EGM is good because it avoids root finding iterations. So let's keep that. And also it would be nice to be able to treat the credit constraint in the same way, even though even in presence of discrete choice. So the idea is this: let's do EGM step for each discrete choice separately, one by one. Okay. Then we can compute the choice specific values for different choices, for retirement and for working. And then we can compare the D-specific values, right? In order to find where the value is higher to be a worker or to be a retiree. And then we can just, find that optimal switching point where at what level of wealth you are willing to be a worker on one side and a retiree on the other side. And that's just an upper envelope, right? But then we also have to reconstruct the consumption rule because for different regimes, worker and retiree, we have calculated in the EGM step a separate optimal consumption function, the policy function. And now we are combining two of them, splicing them at this threshold. Okay, and so no root finding. Well, we will show that the credit constraints are fine. We need to compute value functions because we want to compare different discrete options. And we need to compute the upper envelope. So that seems to be the additional computational work, but it doesn't seem to be that bad. Okay, now another question is, can we still use the early equation in presence of discrete choices? And fortunately, there's this paper, I don't think it's published still, which actually proves that the early equation holds. There's a special upper envelope theorem that allows you to derive the early equation pretty much in the same way. Okay, so let's proceed. Period T, capital T, you could be a worker. I'm sorry, this is, let me take it back. This is drawn for the worker, for the state where there is actually choice. Okay, the retiree solution is just consumption savings. We've seen that before. So this is for the worker. These are discrete choice specific value functions. The blue one is to be retired. The horizontal line is money again. The green one is to work, right? And you can see that retiring in the capital T is strictly better. Why is that? Anyone? Well, remember I said that the wage comes in the next period. If you decide to work today, then you get wage tomorrow. There's no tomorrow here, so all you get is disutility of work. And that simply shifts the value function down by 1, I guess, so by some amount. Okay, so everybody is choosing to retire in the capital T. Now we move to capital T minus 1 and draw the same picture. You can see that this choice-specific value functions start to intersect, and that's exactly because of this trade-off of disutility of work on one side and wage tomorrow on the other side. And I'm not drawing the green line all the way because that was that credit constraint point. And yeah, you have to have a more complicated routine to draw the continuation in the analytical part over there. But we can see that intersection. All right. So zoom in. This is the upper envelope of the two value functions. Now this is analytical, the part of the upper envelope. And you get your value function. Okay, this is the value function for T minus 1, which is the upper envelope over two choice-specific value functions. And you want to be retired if you're on this side and still working if you're on this side. And it makes a lot of sense, right? If you have very little money in the next to last period, you still want to work, to have something to eat in the last period. Yes. That's a very good point. So yeah, should we put a point in the intersection or not? So let's think about that. These value functions are approximated. They are approximated on two different endogenous grids. So the grids are going to be different on for different choices on M. And then we're using linear interpolation here, right? And in principle, putting these points close together using denser grids, you can have two linear segments where you can calculate the intersection. Okay, it's going to be an approximation still because you're not choosing relying on the concavity of these functions. But yes, in principle, it's a technical question. Should we put a point there, or should we just skip it and say that if the grid is dense enough, it's going to be accurate enough? But this is a very good point. So we are losing accuracy by doing this, right? Because now we have to calculate these intersection points. Okay, so that's it. But you see that the value function now has a kink, has this point where it just switches, right? The derivative switches. If we put together the optimal consumption functions, then it turns out that on the right you want to consume according to this schedule. The vertical line doesn't exist. It's a sloppy picture. And then on the left, you want to consume according to this schedule. And this little square shows the point where you're changing the optimal discrete choice, right? So you're retired here and consuming a little bit less. Well, because you don't have to compensate for disutility of work, right? In order to keep that value up. A little bit on the right, you're consuming a little bit more, but varying the disutility of work. So that's what's happening, okay? That's the nature of the kinks in the value function and the discontinuities in the consumption function. We are comparing different discrete alternatives. But then we go to T minus 2 and do exactly the same thing and just graph it. And suddenly we see this. right, on the choice-specific value function to work. And, you know, we didn't know, we were staring with Bertil into the screen and, you know, what's going on? What's happening there? Is that the plotting problem? Is it the density of the grid problem? And we did different things. And this thing just doesn't go away, this little bow tie. And then you zoom in. And what happens is actually that, you know, our value function calculated with the EGM step for the choice of work just starts doing just jumps, you know, up and down, up and down. And we discovered later that that was because we were sorting the grid points, the endogenous grid points at some stage. And so when they were sorted, then it turns out that there are endogenous grid points here and then here and then here, and corresponding value function is completely different, and it, you know, creates this strange picture. So what's going on? Any ideas? So what then later became the explanation is that the D-specific value functions intersect to create that kink, right? The upper envelope, which becomes the value function in period t-1, has the kink, and that means that the derivative of the value function has a discontinuity, but that translates directly into the early equation. And suddenly, if you just graph the early residuals, there is this range of wealth where the early residual, the difference between the left and right-hand side, so it kind of jumps up. The early equation itself becomes non-continuous. Again, the vertical lines here don't exist. And for some range, you just get two solutions. Like for this green line, you get 1 and 2 solutions of the early equation. And that creates these two corresponding levels of value, right, for the value function. So what's going on is that the EGM steps very accurately, you know, traces out all solutions of the early equation, even if there are multiple solutions for some levels of wealth. And that creates that bow tie picture. And so what do we do with that? Well, and what is the nature of this phenomenon? Well, the problem, because in capital 2, the value function has a kink and it's not concave anymore, right? The problem is with the first order condition is that it's not sufficient. And so some solutions of the first order condition, the early equation, correspond to suboptimal levels of value, which are drawn over here. If we, you know, then we killed the sorting, and it turned out that what was happening is that we were producing dots using EGM step, and then at some point just kind of jumped back over here and then continued producing dots going forward. Now, what should we do with these regions? How should we deal with the fact that some solutions of the early equation correspond to the suboptimal levels of consumption and the corresponding value? You know, just looking at this picture, and again, this is wealth on the horizontal, and I'm plotting value function on the vertical axis. Well, the solution is, you know, we are maximizing within Bellman, we're just choosing the maximum value every time, right? The solution is just to calculate the upper envelope. And by the way, see here, we put that little dot here, the intersection. So now the solution to this, to the fact that the early equation have multiple zeros is that we have to do the secondary envelope calculation to filter out the suboptimal solutions of the early equation. Does it make sense? All right.
Well,
And
the way Fedor put it at the time, that's how you know we're willing to work for the good guy, is we need to find the upper envelope in 6.
the exact region, yeah. Okay, so now the algorithm looks like this. Wait a second. Okay, no, let me talk about this first. Can we actually detect these regions algorithmically? Can we write a code that would detect these problems on the fly? The answer is yes, and the foundation is again some the conditions on the utility functions similar to what we had before in the same sort of monotonicity. So it turns out that it still holds in this formulation, and that means that if we generate the points on the savings grid in the ascending order, we expect the corresponding points on the wealth grid to be also coming out in the ascending order. But once that breaks, we know that there is this suboptimal solution that we've encountered. So going back to this picture, well, rather going to this picture, there are indices here. So we first generate this point, and then we take a little bit higher A, generate point number 2, a little bit higher A, point number 3, and so forth. And after point 11, suddenly point 12 corresponds to a lower level of M, of wealth. And that's exactly corresponds to these regions where the correspondence now that is produced by the EGM step as a parametric curve, right, bends back on itself. And because we can detect these jumps back, we can actually detect these regions, right? And start our upper envelope procedure to calculate the upper envelope over all these points, and essentially throw away points 8, 9, 10, 11, 12, 13, and 14. And now where we combine the corresponding optimal savings choices, so the policy functions in savings space, then we already know that point 8, 9, 10, 11, 12, 13, and 14, they're going to disappear because they are suboptimal. And that also breaks this problem with the fact that the policy function is now a policy correspondence rather, right? So we can, using the secondary upper envelope step, we can filter out the suboptimal points from both the value functions and the policy functions. Okay, but going back to the graphs of the value functions, what we now get is that we have this, what we call the primary kink in the value function. That's the kink that corresponds to your being more optimal or optimal on one side to be a worker and the retiree on the other side. And then also the secondary kink, which is just an echo, right, of the primary kink in the next time period. And correspondingly, we get the second discontinuity in the optimal consumption function, which corresponds to that secondary kink. Okay? Do you see where it's going? We're doing backwards induction. So these kinks and discontinuities just accumulate through our backwards induction steps, and you get something like this. So suddenly, the last time period, the optimal consumption is just nice 45-degree line, one discontinuity in the capital T minus 1, and then you go and accumulate these discontinuities in the optimal consumption function. And that pretty much looks like the solution, the analytical solution that I showed you in the very beginning. If we look at the optimal thresholds of when to retire, now wealth is on the vertical axis here, and this is just time periods. You can see that it's optimal to retire at any level of wealth in the end, and then this creates this expected pattern that you want to retire when you have enough money early in life, right? So the retirement age is higher for those who have more wealth for any given time period. Now, if we're looking at the algorithm, at the steps of what now we have to do to solve this problem, well, we just learned that we need to do the secondary upper envelope. So that's an addition that allows us to clean the discrete choice specific value functions of the suboptimal points produced by the EGM step due to the fact that the first order conditions are not sufficient. All right. Now, the problem is that the discontinuities accumulate. And so to take this to any sort of computational work, now you have to be prepared to work with kinky and discontinuous functions. And numerical methods usually don't work all that well. A way out would be to trace the locations of the discontinuities and then work with these functions kind of section by section. But because they accumulate, then, it becomes pretty complicated process. All right. Yeah, let me show you this keen test for the retirement problem. So I'm going to set up the retirement problem with the same restriction that the discount factor is equal to the 1 over 1 plus interest. And so if in the absence of the discrete choice, we would expect to have completely flat profiles. And let's see, these are the solutions. And you can see that for the retirement part, they're just the same as before. For the workers part, we have all these kinks. And these are corresponding value functions for the two states, worker and retiree. These are the choice probabilities, which are just jumps, right? These are the thresholds at age at which you would retire in different ages. And here's the flat consumption profile. The cool thing about this is that these dash lines, I don't know if you can see them, the vertical dash lines, they correspond to the point where this simulation decides to retire, or the simulated agent decides to retire. So they are so rational. And remember, there's no shocks in this problem. Everything is deterministic. But they are able to calculate their optimal consumption from the very beginning of their life all the way to the end, together with the retirement decision, in order to keep that consumption profile absolutely flat over the life cycle. Okay. I have about 25 minutes, right? So now let's talk a little bit about what happens when we include shocks. And so first, let's see if the returns are random. You know, the general picture is that some of these kinks are going to be smoothing out, right? That's what you would expect if there is no way to exactly predict in the next time period where that kink is in the value function and the discontinuity in the consumption function. Then if there's some randomness, then this echoing of kinks, the secondary kinks, will start to be smooth. And that's exactly what we see here. So if we add a little bit of shock in the returns, then you can see that the optimal consumption function has this middle kink, and this is capital T minus 3, as you would guess. It starts to smooth out, you know, and this is the phenomenon that we see if we plot a few of these. But these vertical lines, which are hardly visible, they correspond to discontinuities. Still, there can be discontinuity because there still can be a kink in the value function, even though we've added some shocks to the returns. So I guess the general conclusion here is that, you know, these shocks help, but there's no guarantee that all of the kinks are going to be smoothed out. Like, for example, here with sigma 0.2, we still have a discontinuity, but if you crank it up just a tiny bit, then this becomes completely smooth, this one. And, you know, that's just to illustrate the point that we can't just rely on the fact that there is randomness in the model for these problems to go away. Okay, and another thing to note is that let me see, the secondary kinks can be smoothed with the random returns. But the primary kink, where we compare the discrete options of retirement and working, it will remain in this formulation because there's no way it can go, it can disappear, right? You always, even if the returns are random, you will still be comparing two discrete options. All right, so let's try to also, you know, come up with something to smooth out this primary kinks, this discrete choice kinks. And of course, the solution is, you know, extreme value as the new normal. As you would, you know, learn. We should make this T-shirts, you know, a certificate at completion of the DSE course. And so we need to rewrite the problem a little bit. So now it's going to have the sigma is going to be a scale parameter on the extreme value discrete extreme value taste shock, right? Epsilon over there, and we're writing the deterministic part of the values function, which becomes the choice specific value here as the one with two W's, or W and R. Now, the first W refers to the state. This is the choice specific value function for the worker to remain working. And correspondingly, the choice specific value function for the worker to take retirement. All right, and everything else is pretty much the same as before. Of course, with these distributional assumptions, we get the log sum for the expected value function and the larger choice probabilities. This is an illustration to show you, you know, what happens if we introduce the smoothing. It's interesting to know that if we try to write the early equation in the previous formulation, it is discontinuous, as I've shown you. And you can think of this as being, you know, take the normal early equation, but then it's unclear which region of optimality of the discrete choice you will happen to be in the next in the period t+1? Is it that to stay working or to retire? And that's you know, discontinuity in that place into the discontinuity in the early period. This is just the intuition. But for the smooth version, you can actually derive this early equation, which now have the choice probabilities in the next time period, and you're smoothing between the marginal utilities of worker and retiree with the choice probabilities instead. You know where it's going? It's going to the situation where the early equation now may have three solutions, right? So you have a little bit of shock. Note these shocks here are the black dashed lines, a little bit of extreme value shock. And remember, sigma is now this scale parameter. We add a little bit of logit randomness, and we get this red line for the early equation for a particular level of wealth. And on the horizontal, as you can see, is consumption. And we're solving this. We're solving this for zeros. Now we have three solutions of the early equation. We may, right? But with sigma 0.1, then the whole problem goes away. Well, let's look at what happens to the algorithm. Well, we have rewritten the problem essentially in the choice-specific value function space, and therefore calculating of this switching points and reconstructing the optimal consumption rule from the pieces is not needed anymore. We just do the first four steps in the choice-specific value function. It becomes somewhat harder because we need more space, right? More memory is required, we've effectively made the dimensionality higher for this problem, but you know, we have to do that sometimes. But the calculation of the primary kink in the upper envelope is just replaced by the calculation of the log sum, right? So this is a standard way to take a deterministic discrete choice problem and transpose it into the expected value function space. This is exactly what you would expect to happen. But we still have to do this secondary upper envelope over the zigzag regions. Why? Because it might not be enough of the logit shocks that we've added to actually smooth out all of the kinks of the value function. So there can still be discontinuities in this problem. The good news is though that they cannot accumulate perfectly anymore, right? Because they cannot multiply with this in the same way and to the same amounts as in the deterministic problem. We can also say that you know, it's possible to treat this logit error as just a smoothing device, and we have an upper bound on this introduced discrepancy in the value functions, which is quite a simple formula depending on the number of choices. Any questions? Right. Another point to make is that if we have a combination of shocks, the extreme value shock on the discrete part and say stochastic returns, then this combination works even better. So the problem smoothes out, you know, you can smooth out the primary and the secondary kinks together. And even though you still have to do the upper envelope calculation, now because you don't have this accumulation of discontinuities and kinks, then the numerical work with these functions becomes much more manageable. I guess that's the point. All right, let's see what's going on with credit constraints. I'll just, in the interest of time, show you the picture. So now we have the same story with the credit constraints as before, right? We have some point after which the value functions, these are now discrete choice specific value functions, become analytic in this part, right? And they may have different optimal levels of wealth to save zero, right? To consume everything. So this is the point where the credit constraint just starts binds on all of this region for the retirement choice, right? And that's the one which binds for the working choice. But I guess what we can say is that in this region here, we have analytical expressions for all of these value functions. And moreover, if we have the additive separability of the utility function such that the part of the utility corresponding to the discrete choice is separable, then you can see that this now becomes the same function u of m, the part of the utility corresponding to the money to consumption with some shifter depending on the discrete choice. In other words, in this region here, where all credit constraint bind for all the discrete choices, you can have the situation where these functions are just shifted, the same function shifted up and down. And that, of course, implies that they don't intersect there and the choice probabilities don't change because we're taking the log sum essentially between these two, right, to calculate the choice probabilities in that region. So we can still work with this standard credit constraints. Maybe I should skip that. Well, let's run it once. So there's this implementation for the extreme value smoothed retirement choice, and it produces some nice choice probabilities. As you could see here, these are the choice probabilities of retirement in different time periods. Different colors correspond to different this is the choice probability of staying working, right? Probability to remain working by age. And so this 0 here, or very low rather, is the probability of remaining working in the last time period. Of course, it's very low, but not 0 because of the assumptions on the extreme value, right? Even when it's optimal to retire, then the small probabilities may still be working. And then you can see all this choice probabilities evolving over the life cycle. As before, the idea is that in capital T minus 1, the probability of remaining working is high for people who don't have enough money, whose wealth is really low. You have these pictures for simulated wealth profiles, and this is end of period wealth after consumption. As you can see, there's some stochasticity in the main part, in the active part of the life cycle for people to accumulate wealth, and then everybody retires in different ages, and then they perfectly consume the accumulated wealth to get it 0 in the last time period, and this is of course because they know exactly when they die. We could include the surviving probability and then get bequests and things like that. And these are the corresponding simulated consumption profiles. Everybody smoothing in the beginning, sort of in the same region, but then some people get a series of good shocks and maybe retire early, like this simulation over here, and remain with very high consumption in their retirement. And some people get negative shocks. And and they're here, for example, that's a negative shock also on the retirement choice. So for some reason, this person had to retire at a pretty early age, maybe disability or something like that you can think of, and then remain on the low consumption profile for the rest of life. So as you can see, this framework, even in this very small stylized model, can generate some interesting variation in the simulated data. And then, of course, you get the distribution of retirement ages, which you can also plot and work with. Okay, how much time do I have? 15 minutes? Let me spend a little bit of time on multidimensional generalizations. So this approach is so good that we should use it more, right? Well, the catch is that it's quite special. It applies to the models which it can be applied to, and then for more rich and interesting models, maybe not so easily. So let me explain. The first paper that tried to do the two-dimensional EGM was Barillas and Villaverde, Fernandez Villaverde, 2007. What they had an optimal choice of labor supply, I think, with consumption. And the approach is that you can solve for one of the choice variables separately from the other one and iterate between the two. And so for their particular example, it turned out that the VFI with respect to the, I think it's labor supply, was converging very fast. And then all the action was on the side of the consumption savings and where EGM was applicable. And this transition between the two solvers did not have to happen too many times, because that's the overhead now. Ludwig and Sean, they had basically taken this problem at the face value and compared several approaches of how EGM can be applied. The problem, of course, is that if you have endogenous grid in multiple dimensions, then you end up with non-regular grid in multiple dimensions. How do you interpolate anything on this grid? That's the computational problem in itself. Okay. the correct approach, or what the kind of go-to method is triangulation, Delaunay triangulation, where now to calculate something in between of these irregular points, you're finding the triangle, the 3 points from which to interpolate the interior of the triangle. But computing or separating the space into this simplexes is a computational problem in itself. Okay, so a lot of effort in generalizing endogenous grid point went into trying to come up with some alternative ways to interpolate on the irregular grid that would not be too computationally costly. And so there is a paper by Matthew White, 2015, where he comes up with an algorithm to kind of map the irregular squares into the regular squares, then do interpolation here on the simple square, and then perform the inverse transformation to get back to the. And I guess it's unclear how generalizable this is, and how can you define robustly this nonlinear cells. All right, then there's a paper by Jeppe Druedal and Thomas Jorgensen in Denmark. This is probably the paper which is most general in trying to take EGM to multiple dimensions and occasionally binding constraints. I think that's in the title, right? Non-convexities and constraints. So here the idea is that, remember how we did EGM step for each separate discrete choice? Okay, they're taking it further and they're saying, okay, we're going to have different constraints, and we will have combinations of different constraints, where a discrete choice can be one of the constraints, or a credit constraint could be another constraint. And they're looking at the combinations of various constraints, and each combination is, as far as I remember, is called a segment. And they're doing EGM step for each segment. Each segment then produces endogenous grids in multiple dimensions. And then what they propose to do is to basically recalculate the solution from each segment onto the regular grid, and then you can do the upper envelope, right? Each of these segments produces some surface in the value function space on the irregular grid, and you have to calculate the upper envelope like we were doing, but we were doing it in one dimension. Now they have to do it in multiple dimensions. And so what they propose is to just recalculate, interpolate the computed functions, value functions on the regular space. And of course, this is going to be very expensive in high dimensions. But you can do it in I think there are applications in 4 dimensions in the paper. But here's an application with 2 dimensions, and look how crazy this optimal consumptions, I think it's optimal consumption and pension contribution. So the model here is that you can just save in a bank account or send money to the pension account. And so you have these 2 different types of savings. And I think this is the optimal consumption function, in the space of savings, and maybe this is the bank account and this is pensions, or the other way around. And this is next period pension wealth. This is solved using the first order conditions like we were doing, but now because of the multiple dimensions, it becomes this really complicated. Instead of discontinuous one-dimensional function, becomes this crazy picture. Okay, now another question that the literature has addressed was, what is that class of problems where we can apply this nice trick, right? That's a very practical and important question. And there has been several several descriptions of the class of models that can be solved with EGM. And they essentially, the conditions were, in addition to the regularity conditions on the utility function, you have to have some sort of invertibility or injection conditions on the whole system of nonlinear equations that describe the first order optimality. And I had a little paper in the letters saying that, this is a simple idea that if you have a triangular system of early equations, then you could solve it one by one and back substitute. And you can think of whether there are applications to this particular structure of the problem. All right, what do we do with this, right? I've only talked about how to solve this stochastic dynamic problems. Well, the thing is that we can do this solution very, very fast. Again, if the model fits into this method, then you can solve it many, many times very fast, and that enables you to calibrate, include the solver into the NFXP loop. You can think of any other outer loops where this solver can be a part of, can be on the inside. So you can have some crazy individual heterogeneity, solving the consumption savings problem for every point in your data set is not infeasible, right? Because we can solve these problems, the simple consumption savings, so fast. You can solve it separately for every person in your data set. Maybe there can be, generalizations with random effects or flexible distribution. We can simulate from the solutions of these problems very, very quickly. Let me conclude with this result, which compares actually the estimation exercise, and the comparison is between the MPEC and an NFXP approach with EGM used as a solver. And you can see that EGM approach just blows the MPEC out of the water in terms of time, and that's what you would expect with any other method, just because the solver is so fast. All right, so let's conclude. The points to take home is that EGM and DSE-EGM is fast and accurate solution methods. If your problem conforms to this structure, use that method. Okay. Why? Because no root finding operations and efficient deal, management of the credit constraint. Deterministic discrete continuous problems are hard. It's not because I showed you the example which is hard. They're just hard in general. Okay, they are non-convex and they have these discontinuities in kinks and all this crazy stuff. The snowball effect of accumulation of these kinks is something that we have to deal with in the dynamic world, no matter what solution method you use, right? So VFI will have exactly same problems if you try to solve a continuous discrete problem with just standard VFI. And as always, EV taste shocks, or any sort of taste shocks, but EV are very computationally convenient. They help you smooth out the problems and smooth out some of the kinks and make it more manageable. And so this is actually something that you can work with in actual estimation, actual applications. Questions? Yeah.
So, as the basis of algorithms type of induction, does it work on the finite horizon problems?
Yeah. So yes, that's a very good question. The question is, does it work for both infinite or finite horizon problems? The answer is yes, absolutely. So you can, let me go back to the picture. Well, maybe I don't have to. You could perform the EGM loop, right? Not in the finite horizon setting, but in the infinite horizons and wait for convergence, right? So in general, it is applicable in the infinite horizon setting just as well.
Could you use a policy iteration like John's versus, or is it just?
No, it's better than policy iteration. It's better than value function iteration. We're avoiding any sort of iterative algorithm for fixed points in the fixed.
For horizon, you have a backward induction to find the infinite horizon value function, and then you have the EGM is to optimize.
Okay, I get the question now. Yeah.
Use the EGM inside a policy iteration.
Oh, that's a very good question. Okay.
Presumably you can. It's just the policy improvement step is done by DSE-EGM, and then you get a value function, and then you calculate the implied value function.
So you would have to calculate the derivatives of the value functions, right? Yeah, it's a very good question. Yeah, it's probably worth thinking about whether this can be included in the policy iteration rather than value function iteration algorithm. Thanks, John. Somebody can write a paper. All right, then thank you for the day. We'll see everybody tomorrow at 9 again.